Hey everybody, welcome back to Math 251. Hope you guys are doing well today. In this video, we are going to talk about related rates. So related rates are a kind of problem, often a word problem, where multiple quantities are changing in conjunction with each other. So most of the time, the variables that we have are related to each other in some way. And after we figure out the relationship between the variables, we have a bunch of information that we can plug in and solve for exactly what we want. So the textbook lays out a pretty good step-by-step guide as to how to solve related rates problems. First, we draw a picture and assign symbols to all of the variables that we care about. Then we state the information that is given and the information that is to be determined. So we want to write down what we know and what we want to know. Then we find an equation that relates all of our variables together. After that, we introduce related rates, which are these, rates that are changing with each other by differentiating both sides, and often we have to use the chain rule. Finally, we plug in all of our known values and solve for our desired quantity. So let's do a couple of examples in order to figure out how these steps come into play. So first of all, a cube is inflating at a rate of 20 cubic centimeters per second. When the side length is 30 centimeters, how fast is the side length changing? Okay, so first things first, let's draw a picture. I am not good at drawing cubes, but let's give it a try. Okay, we'll pretend that's a cube. So we have a cube here, and it's inflating at a rate of 20 cubic centimeters per second. Well, let's label some quantities here. This is a cube, so all of the side lengths are the same. So we'll label the side lengths of this cube L. So L is the side length. And what else do we have? Well, we'll call V volume. So in the first sentence here, we have the cube is inflating at a rate of 20 cubic centimeters per second. That means the volume is changing at a rate of 20 cubic centimeters per second. Now, whenever you hear the word changing or rate in these problems, that should be a giveaway that that is a derivative. So our volume is changing at a rate of, that means that this is the derivative of the volume, 20 cubic centimeters. So this is the information that we know. What else do we know? Well, we care about when the side length is 30 centimeters. So I'm going to call L 30. What do we want to know? We want to know how fast this side length is changing. Now there's that word changing again, so that means that this is the derivative of L as time is changing. Related rates almost always have to do with time as our variable. Okay, so here's what we know and what we want to know. Now we need to find an equation that relates our two variables together. So how are side length and volume related to each other? Well, since this is a cube, I know that volume is equal to L cubed. This is the equation that we'll be working with. So now I want to differentiate both sides because I have some derivatives here that I care about. So I need to differentiate both sides, but I need to keep in mind that L is a function. The side length is changing, it's not static. So I need to use the chain rule here since L is a function and not a variable. L is a function. So using our chain rule here, that means our outer function is x cubed and our inner function is L. And f prime is equal to 3x squared. And g prime is equal to dl dt. So when I differentiate both sides here, on the left side I get dv dt. And on the right side I get f prime of g, that's 3l squared, times g prime, that's dl dt. And I'm trying to solve for dl dt here. So if I shift this around a little bit to solve or isolate for dl dt, I get dl dt is equal to dv dt divided by 3l squared. From here, I can plug in all of the information I know. I know that dv dt is 20 and L is 30. And when I plug this into my calculator, I get 0.0074. What is our unit here? Well, our length is changing at a rate of centimeters, and our time period is second here. So this is how fast the side length is changing when the side length is 30 centimeters. Um, and let's just check on this. Does it make sense that this is positive? Well, yes, it does make sense that this is positive because if the cube is inflating, that means that the side length is increasing, so that the derivative of the side length should be positive. Okay, let's do one more example. An oil spill occurs in the Pacific Ocean, and the oil spreads in a circular patch. The radius of the circle increases at a rate of 50 feet per minute. When the area of the patch is 1,000 square feet, how fast is the area changing? So here our picture is going to be a circle, and let's call the radius r, and I'm going to call the area, that's the other quantity that we care about, the area I'm going to call a. All right, what information do we know? Well, we have the radius of the circle increases at a rate of 50 feet per minute. That means that the rate, or the derivative, of the radius is 50. And we also know that the instant that we care about is when the area is equal to 1,000 square feet. And what do we want to know? We want to know how fast the area is changing. That word changing there tells me that I'm searching for dA dt. Okay, well, how are my variables related to each other? How is radius and area related to each other? Well, I know that area is equal to pi r squared. Remember that r is a function here. R is a function. So when I take the derivative here, as I need to do since I have a bunch of derivatives that I know, I need to be sure to treat r as a function and not a variable. That means that I will, of course, have to use the chain rule on r squared. So when I use the chain rule, I am left with dA dt equals pi, and then when I use the chain rule, I get 2r, that's f prime of g, times dr dt. So this is what I get after I differentiate. And we are looking for dA dt. Luckily for us, this is already solved for dA dt. So now I just plug in everything that I know. However, we have an issue here because here in my equation, I have the radius, and the other piece of information I have is area. Well, that's okay because we know the relationship between area and radius, so I can solve for the radius that we are concerned with. So I want to know the radius when the area is equal to 1,000. So I know that 1,000 equals pi r squared. We're trying to solve for the radius. If I divide 1,000 by pi, I get 318.3 is equal to r squared. And if I take the square root of this, I get 17.84. So when the area is 1,000, this means that the radius is equal to 17.84. So sometimes we have to use these relationships in order to solve for other quantities, but that should be just fine. All right, so let's plug in what we know here. This is pi times 2. We just solved that the radius was 17.84 times dr dt, which is 50. So if I plug all this in, I get pi times, pi times 2 times 17.84 times 50. This is equal to a big number, 5,604.6. What are our units here? This is dA dt, so our area is changing at feet squared, and our time unit is minute. So when the area is 1,000 square feet, the area is changing at a rate of 5,604 feet squared per minute. And that is a short and sweet introduction to related rates. Hopefully you learned something in this video, and I'll catch you later.